Cisco instructor Andrea here, and this is a video review for the Introduction to Networks course, Module 3. Module 3 is all about network protocols. Let's take a look. Before we get started, I always like to give you a reminder that this is a good time to check on your grades. Make sure you're reading all of the comments that we put in there. Also, look at the view feedback. And just ask yourself, are you keeping your study plan? And are you keeping the schedule that you committed to keeping so that you can do good in this class? After you read the comments on your grades, if you have any questions, just let us know. Also check the discussion board and any announcements that we might have posted. Another thing I want to remind you to do is often we have posted required videos that are related to binary to decimal or network addressing. Make sure you're always watching those before you come to class, because that will make our discussions about them and our practice and our demonstrations much easier. The Module 3 preview listed out a lot of different things that you would want to focus on for this module. So what are the 3 fundamental requirements common to all communication methods? What is encoding and decoding? What is the importance of a frame? Can you describe encapsulation? What are the 3 different delivery methods? What is a default gateway? What are the network standards in the organizations that set them? Also, watch the binary videos. What are the 2 most common protocol suites? You want to know them in each of their layers. What are some of the common protocols that function at each layer within those protocols? Can you describe what the PDUs are? Why does networking use segmentation and multiplexing? What is the address at the data link layer? And watch all of the videos inside of the modules of Netacad. Those videos are super helpful. So as you're reading the modules, also make sure you're watching the videos. I want to remind you, this is not an exhaustive list of everything that's important in Module 3. It's just some of the highlights. So when we're talking, if there's anything that you have questions about, you can bring them up in class, or follow this up with the reading assignment and see if that helps you. A group of interrelated protocols are necessary to perform a communication function called a protocol suite. So basically, a protocol suite is a way to define the way data moves through our network and how data allows us to communicate from the source to the destination. So we know that it takes networking devices to allow data to move across the network, but understanding the different things or the different mechanisms at each layer is also important to knowing how data moves through our network. So this group of interrelated protocols, the protocol suite, have different rules at the different layers, just like traveling would. So if you're traveling in a car, you have to obey stop signs, traffic lights, speed limits. So there are rules and regulations that are set up for the way data moves through our networks that dictate how the data moves and how the traffic will flow. So just like different types of transportation in our city, they need a way to communicate with each other and also to keep track of everything. So we need to know, like, if the bus is moving one direction and a car needs to turn, there needs to be some sort of stoplight or mechanism for the timing to be right for all of these different types of transportation to happen. Well, the same thing is true on the internet. If you can think about all of the millions and gazillions of people that are using the internet at the same time, there have to be some rules, regulations, and timing to regulate that traffic so that there isn't traffic jams or congestion. So the protocols will describe a framework of network rules and functions. Again, this is just an example. It's like a train or a light rail. will have one set of rules. A regular steam engine train, that would follow a different type of rules and go over a different type of track. This is here a bus, right? Same thing. A bus is going to follow different rules and regulations. That is the way the internet works. What are the three fundamental requirements common to the communication methods? So same thing, if you're thinking about traffic, there's always a starting point, there's an end point, and then there's whatever we traveled on. If we are traveling by train, we get on at the starting train station, we travel across train tracks, and we get to our destination. Traffic for the internet is the same way. Different types of transportation in a city, you're going to have a source or the beginning of the communication. We're going to have a destination or the end of the communication. And then we're going to have the channel or the media, the connection that runs between the source and the destination. If I'm writing an email and I'm sending it to you, I am the source device. My computer would be the source device. It's going to go out across the network, whichever the different channels might be, until it gets to you, the destination. Protocols establish a lot of different parameters for communicating across the network. The first thing, or one of the things, it's not necessarily first, is something called message encoding. Now, along with that, there could also be message decoding, message formatting and encapsulation, message size, message timing, and then the different delivery options. These are all pre-established things that protocols will take care of. Here's a good question related to protocols. What is the process of converting information into another acceptable form for transmission? One of the things I want you to do in this class is start to learn how to break questions down, because sometimes they may sound a little bit confusing, especially if you're not exactly sure what they're talking about. So what might be getting converted here? If you think about networks and networking devices and computer devices, their language, if you will, is bits, ones and zeros, ones and zeros, ones and zeros. And that's all that they know, and that's all they know how to read. If I'm sending something from my source device to your source device, my computer and my NIC card is doing everything in bits. But when it hits the Ethernet cable doesn't necessarily understand ones and zeros, but it will understand electrical impulses like on and off, on and off. Well, that process is called encoding. When the bits get encoded into another acceptable form for transmission across the media. So each bit is encoded into a pattern of either electrical impulses, which would be like on, off, light waves, okay, which is also a type of on and off. The light goes on, the light goes off. Or sound waves, radio frequency waves. And what that is dependent upon is what your media is. So if it's Ethernet cable, that's copper or coax, it's going to be electrical impulses. If it's fiber optic, it will be light waves. If it's radio frequency, wireless, it will be sound waves. On and off, okay? So here's what we start with. We start with the bits, ones and zeros, and that is going to be encoded into electrical impulses, on, off. Or it might be where we have like these three ones together, on, and then an off, and then an on, and then there's four offs. Okay. Here's another example of light. This would be like a laser light or an LED light going across a fiber optic cable where we see these waves of light. Again, we've got our bits, and now we're going to encode it into radio frequency waves. And again, this would be like a sine wave, and the dip is the 0 and the peak is the 1. The dip is the 0 and the peak is the 1. When the traffic, the data that I'm sending from me to you, arrives at your location, the reverse happens. The electrical impulses get de-encoded or decoded, and they get decoded back to ones and zeros, ones and zeros. The rules of encoding, formatting, and encapsulation. The first step in sending a message. This message doesn't necessarily have to be an email. It's any type of data. I like the analogy of an email because I find that easy to explain and easy to visualize. So the first step is sending a message, that's encoding it, the process of converting information into the acceptable form of transmission across the media. It goes across the media, it gets to you, it's decoded, which reverses the process in order to interpret the information. Each computer message is encapsulated into a specific format called a frame. We will be talking about frames a lot because the term frame is referring to a PDU at the layer 2, the data link layer. What the frame does, so we take the piece of data, we put it or encapsulate it into something called a frame. The frame is going to have some information. It's going to have the destination, so where I'm trying to send it, in this case, if it's you, okay, and then the source, that would be me. The format and contents of the frame are determined by the type of message being sent and the channel or the media of communication. This is just kind of an example, right? Again, if you think of it kind of like a letter, or even an email. I'm going to address the email to you. It will be from me, and it will get sent across the media or the channel. This question is to check to see if you are keeping track and taking notes. The special format that each computer message is encapsulated into is called a what? A packet, a frame, a byte, or a code. Now, hopefully this is easy for you because really we haven't touched on packets, I don't think. We have talked about frames. We've talked a little bit about bytes probably in class, and I've never heard of anything as just referred to as a code. Did you get frame? If so, you got it right. So I'm recapping here. Each computer message is encapsulated into a frame. The frame provides address of the destination and the source. The format and contents of a frame are determined by the type of message being sent and the channel used in communicating. Usually when I have multiple slides for the same topic, it's because you will see that on quizzes, brain teasers, and most likely the CCNA exam. And I just want to drive that point home. Again, here's our frame with our source and our destination. Know the importance of a frame. Know that the frame is also from layer 2, the data link layer. Something else that happens as data moves through the network is it goes through a process of getting divided into more manageable pieces in order to send it across the network. So what is this called? The process of dividing. Think about some of these words and see if you can do a breakdown in a process of elimination. We have encapsulation. Now, we already talked a little bit about encapsulation, that's the process of wrapping up a frame, right? So it probably doesn't have anything to do with dividing. Next, we have the term segmentation. We have de-encapsulation or transmission. Did you pick segmentation? If you pick segmentation, you would be right. Remember, protocols provide message timing, formatting, the size, and that's where this comes in. There's size restriction of the frames. When we're sending data across the network, I can't just send 1,000,000 bytes and one long message stream. 10100011. I can't do that. So what we have to do is this data has to get chopped up, okay? It has to get chopped up and segmented so that it can be forwarded across the network. Same thing with a giant email that I would be sending with lots of data and files. It'll leave my network and it's going to get segmented so that it can move across the network, right? This is called segmenting. Each segment, so after it's segmented, that segment gets encapsulated into a frame. Okay, so let's say, I'm just going to make up numbers. Let's say I have this long piece of data that needs to be sent from me to you. It's going to get chopped up into 100 pieces, okay, segmented into 100 pieces. Each of those 100 pieces is going to get encapsulated into the frame. Each of the pieces will have the source and destination. So it's going to have me as the source, you as the destination, and the pieces will be numbered with a tag 1, 2, 3, 4, 5, all the way up to 100. The reason it gets tagged with that number is so that the pieces can be tracked. That way, the pieces might all move over different lanes, if you will, okay, across the internetwork. When it gets to you on your side, all those pieces have to be put back together. Having the numbers 1 through 100 allows them to be put back together. Why does networking use segmentation and multiplexing? The reason is for efficiency and speed, okay? Efficiency and speed. Here's an example of one big piece of data. That isn't going to work. So instead, we chop that one big piece of data up into several different pieces. Each of those pieces is called a frame. Each of those pieces get a numbered tag and then also the source and destination address. As you can see, this might be a good time to take a break. So if you need to walk away, stretch, use the restroom, this is a good time to do that. The rules. Remember, protocols set up rules. One of these is timing, how data is going to be timed across the network. Think back to the transportation analogy. If the light rail in Phoenix and a car is going the same direction and one of them need to turn left or right, we don't want them to cut each other off or cause an accident. So there will be some sort of timing where a light will turn red for the light rail so the car can go, or vice versa. The same type of thing happens over the internetwork. Data gets timed. There's message timing so that there aren't collisions of data. And because if there's collisions of data, the data doesn't arrive at the other end. So number one rule of engagement is to have an access method. Hosts on a network need to know when to begin sending messages and how to respond if a collision does occur, okay? So the host will be like thinking, can I send a message? Can I send a message? Can I send a message? Plus, there needs to be something in place that if it sends a message and there's a collision with another message preventing the data from getting to the destination, the device needs to know, well, what do I do? The source device needs to know, what do I do for that? Flow control. Source and destination hosts use flow control to negotiate the correct timing to avoid overwhelming the destination and ensure information is received. So if you think about these frames going out on the network, right? There's a frame, there's a frame, there's a frame, there's a frame, a frame, a frame, a frame. The destination device needs to be able to receive these frames or receive this data, okay? And sometimes one device may not be as quick as another. So the source has a way of assessing the traffic and how much congestion is out there, and it can modulate what it puts onto the network. And that is called flow control. It's controlling the amount of data or traffic it's going to send out. Lastly, there is a response timeout. Hosts on the network have rules that specify how long to wait for responses and what action to take every response timeout occurs. In other words, I'm the source, I'm sending out data, and nothing's coming back. I'm going to make an assumption as the source device that whatever I'm sending out is not making it to the destination I intended for. So I'm going to wait a little bit as the source device. And then if I don't get a response back, I'm going to resend it. Okay? So those are the rules for timing, the rules for engagement of data that's crossing our networks. This slide is about the delivery options, the different ways that the data is delivered at the other end. What are the 3 different delivery options hosts and other networking devices use when transmitting data and information? There's 3 ways: unicast, multicast, or broadcast. The next question is a matching question. So what are these? What does unicast, multicast, and broadcast mean? Let's think of unicast first. Uni means one. As we look at these options, a host needs to send a message to a group of hosts. This would be one to several, so host to several. The next option is a one-to-one delivery option is used. Lastly, a host sends a message to all other hosts. Unicast, I hope you picked a one-to-one delivery option. One-to-one delivery option would be like me sending you an email, okay? Just one person to another person, or one device to another device. How about multicast? A host needs to send a message to a group of hosts, one to several. So it's one to several, it's not one to all. This would be an example of, let's say we're in class and we have half the class sitting on the right side of the room and half the class sitting on the left side of the room. Well, if I want to send a group email or a group message to everybody on the left, that would be considered a multicast message, because some people will be getting the message, but not all people will be getting the message. Okay? And then lastly, we've got a broadcast message. This is a host sends a message to everybody. Okay? Everybody. This is also referred to as a broadcast domain. I want you to remember that terminology, broadcast domain, because that's going to come up in some future modules and it's going to be a really important concept. Hosts also have requirements for acknowledged versus unacknowledged messages, just like the post office would send a certified letter or maybe an uncertified letter. So depending upon the message that we're sending, that data may require a response, like sending out data, and the receiver or the destination will send an acknowledgement, letting the sender know they received that message. Here's an example of a unicast message. Here's my source device. They're going to be sending out a message, and it goes to one destination. Here's an example of multicast. Here's my source device. I'm sending that same message to two different devices on my network. Or lastly, a broadcast. Here is my source. Now notice this message got sent to every host on the network. It was broadcast out. What are the two most common protocol suites? The OSI model, and there's 7 layers in the OSI model. And the second one is the TCP/IP model. This is 4 layers. The reason we have protocol suites or models is because this explains the way that data moves through the network. At each layer, something different is happening. And at each layer, there will be specific protocols that function at those layers, as well as standards that have to be met. Let me give you an example. If you have an Android phone, the way that you charge your phone now would probably be like the USB micro C. And the old, from a couple years ago, it was a little bit different style. Well, standards dictate that all Android phones have to have the same type of adapter for charging the phone. Apple OS phones, Mac phones, they have to have the same type. Not the same type as an Android, but the same type as all their other phones. Phones can go through changes, okay, where they might upgrade or update this, but then they need to update all the phones. You may not know this. It depends how old you are and how long you've been using mobile phones. But 20 years ago, 15 years ago, every mobile phone had a completely different type of adapter for charging the phone. Well, the organization that is responsible for that put a stop to that and said, enough is enough. All of you need to come up with a standard and make all of your phones have the same type of charging adapter. Now you can apply to get it changed or updated. And if we approve that, then you've got to do it across all your phones. And you've got to provide a mini adapter for people that would have an older version. That's what OSI layer and the TCP/IP layer does. They create protocols and standards at each layer. The OSI model has 7 layers. I like to remember it by all people seem to need data processing. Okay, those, and I'm going to tell you those layers in a minute. All people seem to need data processing. Now the TCP/IP layer, that is only 4 layers, and it's A, T, I, N. I used to remember it by a tin man. Now the word man means nothing in this analogy, but a tin, A-T-I-N. Why 7 layers and 4 layers? I'll tell you, these protocol suites more or less do the same thing. The TCP/IP layer model is a much older model. It is the model that was first introduced when the internet began to grow and boom, and we needed some sort of organizations and standards to manage it. And at the time, not very many people were using it, and it was simplified, and we didn't have all the technological advancements that we have today. So 4 layers kind of took care of everything. As technology improved, data networks grew, we needed to add some granularity to that and fine-tune things. That's when the OSI model came about. And they described the way data moves through networks with 7 layers. Okay. The top 3 layers of the OSI model, the application layer, the presentation layer, and the session layer, they actually align with the 4th layer or the top layer of the TCP/IP model, the application layer. Again, these two models more or less are doing and saying the same thing. It's just that the OSI model is much newer and gives us some granularity that the TCP/IP model doesn't give us. Okay. A protocol suite, such as the TCP/IP protocol suite or the OSI suite, is a set of protocols that all work together to provide comprehensive network communication services. Networking protocols defined a common format and set of rules for how a message is formatted and structured, the process by which networking devices share information about pathways with other networks, how and when error and system messages are passed between devices, and the setup and termination of data transfer sessions. There are several common protocols used in networking and found within the protocol suites. When I name them, I think you might even have heard of some of them before. At each layer, there are different network protocols that work, and they each have their own job to do. HTTP, Hypertext Transfer Protocol. Ask yourself, where have you seen this or heard this before? This would be when you're accessing a web address, right? You're trying to go out over the internet. TCP, Transmission Control Protocol. You might not have heard of that one before unless you have some computer knowledge. IP, the Internet Protocol. Maybe you've heard of an IP address or an IPv6 address. Well, that is a protocol that goes and fits into the suites. DNS, Domain Name Service. DHCP, Dynamic Host Configuration Protocol. HTTPS. HTTPS is just Hypertext Transfer Protocol with some security added. Here's an example of the TCP/IP protocol suite. And notice here, these are the layers. And we'll be asking you these layers all the time. So you want to start working on memorizing them. The application layer, the transport layer, the internet layer, and the network layer. So for me, this is where that Tin Man, A-T-I-N, a Tin Man comes in. Here's an example at the application layer. These are the different protocols that function at the application layer. The transport layer, UDP and TCP work at the transport layer. The internet layer, IP, NAT, ICMP, several others. And the network access layer, ARP, PPP, Ethernet, interface drivers. This is an example of protocols that work with the TCP/IP model. Now, these same exact protocols work in the OSI model. It's just that because the OSI model is a little more granular, we may see these broken down at a little bit different location. All right, let's do some double matching. We want to match the following layers to the OSI model. With the OSI model, you may see the OSI model listed from 1 to 7, or you might list it from 7 to 1. Once you've been practicing for a while, you'll be able to go both directions. And remember, at each layer is responsible for a different function that happens across our network. Let's start with number 1, layer 1. Which layer is that? Is it the transport layer, the data link, the application, the network, the presentation, the physical, or the session layer? It's the physical layer. It's the physical layer. For a minute, I was almost going to reverse it. All right, it is the physical layer. How about layer number 2? What is layer number 2? So we're going from the bottom up. Data link. Layer 3. Think about all people seem to need data processing, and that's from the top down. So we want to go from the bottom up. Network. 4. Transport. 5. Session. 6. Presentation. 7 is the application layer, the top layer of either the OSI model or the TCP/IP model. Okay, now we have the double match. At the transport layer, what is happening at the transport layer? Is IP addressing happening at the transport layer? Is web browsing happening at the transport layer? Web conferencing? Would we find bits there, port numbers, MAC addresses, JPEG, or PNG? When you don't know the answer to something, see if you can break the word down. In this case, transport. I remember seeing something over here with the word port. If you don't know the answer, that could be a good guess. Data link layer. So this is layer 2. So I'm moving from the bottom up. Number 2. MAC addressing happens there. A MAC address is a physical address that all devices have. Next, the application layer. The application layer is the very top layer. And when you think application, you might be thinking an app, okay? An app, or an application, something I can interact with. So this would be web browsing, because that is an application I can pull up, and as the user, I can interface with a web browser. Network layer. The network layer is where IP addressing happens. Presentation. How something is presented to me on my monitor or on my cell phone. If you look at what's left over, web conferencing, bits, or JPEG and PNG. So JPEG and PNG, isn't that like a picture? That could be the way something is presented to me. Physical. So physical is layer 1. Well, at layer 1, that's the layer closest to where you actually plug your cable into your computer or plug your cable into your networking device. And we know that encoding happens in order to convert bits into a format that can move across the media. So here we have bits. Here we have bits. Lastly, a session. That's going to go with web conference. When you open up a WebEx or a Zoom, what happens is you have to open up what's called a session. I think of it like a wormhole. A wormhole or a session has opened up so that I can send and receive information along this session and actually have a web conference. Those are some ways to think about and break down these words. What network protocol affects the way a web server and a web client interact? Think about that terminology and what we just covered on the previous slide. If you thought, oh, web browsing, that's at the application layer, that would be HTTP or HTTPS. Here we have the user interacting with the computer through the world to the World Wide Web with HTTP. What is the form a piece of data takes at any layer? As I send a message to you, that message is going to get segmented and encapsulated, and it's going to start moving through the OSI model or the TCP/IP model, whichever. And as it's moving through the model, either from my source, so it's going from the application to the presentation to the session to the transport, right? As it moves, depending upon where the data is, we in the field of networking and computers call that data something different. At wherever it's at, we just call it a little bit something different. Okay, we call that a PDU, a protocol data unit, a protocol data unit. As application data is passed down the protocol stack to be transmitted across the network media, various protocol information gets added at each level in order to process in a process known as encapsulation. Okay, so as it's moving down the OSI model, it's picking up information. And once it gets that information, it gets encapsulated. Okay, the form that that data takes is called the PDU. Here's our OSI model. I'm right here, okay, at the application layer. As a matter of fact, right now, I'm interacting with my computer at the application layer. And as I am interacting, it's moving the data through the presentation layer, the session layer, and each layer that it goes through, it gets encapsulated and it picks up different information. There are 5 types of PDUs. What are they? 5 types of PDUs. Data, segment, frame, packet. Don't send pets for beer. Data, segment, packet, frame, bits. I remember it by don't send pets for beer. And you can see I messed up when I didn't say the little mnemonic first. Don't send pets for beer. Data, segment, packet, frame, bits. Okay. So here's just a little example. Here's the user sending email. So I'm interacting with an email server in the email client. So at the application, what do we call the data when it first gets to the application layer? Well, we call it data. It's just called data. Now the data picks up information and it gets moved down. Application, presentation, and session are looked at kind of like a bundle, okay? Like a bundle. So we don't have 7 PDUs, we only have 5 PDUs. It gets moved down, so it's already gone through the application, the presentation, and the session. Now it hits the transport layer. What is it called at the transport layer? It's called a segment. So once the data hits the transport layer, we call this a segment. Then we get to the inter-network layer if we're looking at the TCP/IP model. If it's the OSI model, we would call it the network layer. And at the network layer of the OSI model, which is the inter-network layer of the TCP/IP model, we call it a packet. The reason we call it a packet is because that's where IP packet information is added. It's called a packet. Now from the packet, I move it to the data link layer, okay, the data link layer, and this is called a frame. So this is what we were already talking about, a frame, okay? It's functioning at layer 2. It's called a frame. And then finally, it's going to hit the NIC card, or it's going to hit the interface on our router or our computer, and it's going to be encoded into bits, the ones and the zeros, the ones and the zeros. All right, here's a little picture of data moving. Let me see here. I'm going to wait till it comes back over here. Now, what I want you to look at is I want you to look at these little pieces. I know it's moving kind of fast, but it moves across. Now watch, as it goes up, it starts to remove the pieces. Think about this like I'm right here. I'm at the application layer and I'm sending an email. Okay. I'm going to wait till it gets back over here. Now, each layer, notice it picks up another little box. It moves across the media. Now it's trying to come to you. So it's de-encapsulating it. It's taking those little boxes off and reading the information. De-encapsulation is the process used by the receiving device, the destination device, to remove one or more of the headers, one or more of the protocol headers. This is how data learns what its destination is and how to get to where it's going. The encapsulation process works from top to bottom. At each layer, the upper layer information is considered data within the encapsulated protocol. For example, the TCP segment is considered data within the IP packet. De-encapsulation is just the opposite. It's removing the headers so that it can keep pushing that data up to you or the receiver. Okay. Looks like this might be another good time for a break. We've already covered a lot of information in this module. Let's go ahead and just, again, move your eyes away from the screen, maybe stand up and stretch. If there's a piece of advice that I could give you that I wish I would have understood better as I began working in this field, that would be to take more breaks, give my eyes a rest, and work my arms and my movement. This could be a job that you go into and you could work like this for the next 20, 30, 40 years. You want to take good care of your eyes, your neck, your shoulders, and your arms. So let me give you some advice now and start taking care of your physical well-being. There are jobs that are very physical jobs, and those come with some obstacles and challenges too. These jobs can as well. The way that this course is laid out, starting with Module 4, which is the next module, is the course is laid out by the OSI model. Module 4 covers the physical layer. Module 5 covers, that covers something else. But then modules 6, 7, and 9 cover the data link layer and start to move into the network layer. Modules 8, 10, 11, and 12 cover the network layer. Modules 14 covers the transport layer. So each module covers a different aspect of the OSI model. After this explanation of the OSI model and the protocol suites, we start doing that. And so you're going to get a lot more practice with the OSI model and what all of these layers mean. We're going to break this down a little bit further. Which two layers are responsible for delivering data from a source device to a destination device? So there's two layers that have very specific jobs in delivering data from point A to point B. Physical, data link, network, transport, or the upper layers. And here we have a nice little example. Data link and the network layer. The reason is because each of these have addressing associated with them. The data link layer has the source and destination MAC address, and the network layer has the source and destination IP address. Well, these addresses are what's needed to move data through the network, kind of like receiving a postcard or receiving a letter, right? You've got to have a source or a return address and the destination address. That's what's happening with the data link layer and the network access layer. The network and data link layers deliver data from the source device to the destination device. Protocols at both layers contain a source and destination address, but their addresses have different purposes. Network layer source and destination addresses are responsible for delivering the IP packet from the original source to the final destination. A data link source and destination address is responsible for delivering the data link frame from one network interface card to another network interface card on the same network. That's really important. The data link layer only works within its own network. The network access layer, well, that can contact and communicate with remote networks. MAC addresses. We start talking about MAC addresses in Module 6, and then we'll keep talking about them. We talk about IP addresses in Modules 8, 9, 10, 11, and 12. The data link address is the MAC address. Its job is to deliver the data link frame from one network interface to another network interface, again, on that same network. The IP address is the network layer logical address used to deliver the IP packet from the original source to the final destination. Now, does this term packet seem familiar? I hope so, because earlier we said that the word packet was a PDU at the network layer. It's a PDU at the network layer. An IP packet must be encapsulated in a data link frame so it can be transmitted over the physical medium. An IP address can't go over an Ethernet cable, okay? But we can encapsulate it inside the data link frame so that it can be moved down to layer 1 and then pushed across the media. As the IP packet travels from device to device, it gets encapsulated in a data link frame. Routers will remove layer 2 information as it is received on one NIC and adds new data link information before forwarding it out the exit network interface. Here's just some of the things that are happening along the way. At the physical layer, we're taking care of timing and synchronizing the bits. Remember, I can't overload my media with bits 111100001111. I can't overload it. I have to have some sort of timing and synchronization. Data link, that's where it's picking up the source and destination MAC address. The network, it's picking up the source and destination IP address. The transport layer, it's picking up the source and destination port numbers. And then the upper layers, it's encoding all of the application data. Again, just a little breakdown of what's going on at each layer. Remember, every module we're going to talk about is going to be covering this stuff, and we will keep practicing it. Each data link frame contains the source data link address of the NIC sending the frame and the destination data link address. We're going to do some examples of this in class. We're going to actually look at a network and we'll be able to see this information move through the network. And that also really helps to be able to visualize and understand how data is moving through the network. All packets destined to a remote network must be sent to a what? And we'll cover this again in 8, 9, and 10. It must be sent to a what? Now notice this says to a remote network. If I am in my house and I need to communicate from my computer to my cell phone, they're on the same network. It doesn't need to go, that message doesn't need to go to a default gateway. Okay, a default gateway. Oh, I didn't. Okay, the answer here is default gateway. Okay, whenever a message, so when I'm sending a message from me to you, That message first has to go to the default gateway on my home router. Write this down. A default gateway is the entry and exit point to every local area network. Okay? Default gateway is the exit and entry point to every local area network. Every local area network has to have its own default gateway. Okay? When the sender and receiver of an IP packet are on the same network, the data link frame is sent directly to the receiving device. It doesn't need to go to a default gateway. On an Ethernet network, the data link addresses are known as media access control addresses, MAC addresses. When the sender and receiver of the IP packet are on different networks, the Ethernet data link frame cannot be sent to the destination host because the host is not directly reachable in the network of the sender. The Ethernet frame must be sent to another device known as the default gateway, the exit and entry point for all of our local area networks. All packets to a destination on a remote network are sent to the default gateway. We're going to do examples of this in class. We're going to look at labs and packet tracers that also demonstrate this. This sounds all really wordy, even to me. So we definitely want to back this up with some examples and demonstrations. All right, here's a pretty decent picture. Let's say this is me. Okay, here I am. And here's my router. And here is the ISP server. Now this says ISP router because the ISP gave it to me, right? They provided it to me. So if I want to send information and get like to Google, okay, I want to send or I want to shop on Amazon, the packet and the data are going to go and follow this path. And because I'm trying to leave my local area network, that has to go to the default gateway before it can leave and hit the server. Now, if I just wanted to talk to this laptop over here, the data traffic would just go out this Ethernet, it would hit the switch, and then it would just be sent to the laptop. This is on the local area network. Whenever you're communicating within your local area network, you don't need a default gateway. You only need this default gateway, and this has to be functioning whenever you want information and data to leave your network. Oh, we've got a little picture there. That's a local communication, right? That's local. Let's see if I have an example. Oh, and I have an example of it going out. So see how that goes, and then it stops there at the default gateway so that it can get its directions to know how to get out of there. Standards and organizations. This is just an example of some of the different standards and some of the different organizations that are creating these standards. I gotta tell you, you will be asked a few questions on the CCNA about different organizations and the different standards. There's no real easy way to learn them. You have to just more or less memorize them. When it comes to things like the default gateway, that's going to start to become really easy because we're going to set up a default gateway. We're going to look at lots of examples of a default gateway. You're going to get to do some hands-on stuff. When it comes to these standards and organizations, there's no hands-on way to talk about the ICANN or the IANA or the IEEE. My advice is you go to the modules, you read about them, you make notes, flashcards, and you just start committing them to memory. I don't even remember all of them. And what I do before I have to go take a certification exam or an exam, I pull out my old flashcards and I review and I just kind of rememorize them. This is just another word about the OSI model. It is the most widely used and known reference model. There is still talk about the TCP/IP model. It's just not as descriptive or granular. So most often when you hear people talking about a protocol suite, they will be referring to the OSI model and the way that data moves through the OSI model. We will forever be challenging you to know it. We'll be asking you to call it out in class. So again, just go ahead and commit this to memory. I wanted to point out that the two most common troubleshooting issues are what? And this is going to come up in class all the time. Whenever a packet tracer doesn't work, whenever a lab doesn't work, the first thing we're going to do is we're going to tell you to check your IP addressing. And the next thing we're going to tell you to check is your media connections, all of your cable connections. These are the two most common problems. And the good news is they're actually some of the most easy ones to fix. In Module 2, we already started talking about IP addresses. I think even in Module 1 we did. We're going to just talk a little bit more about it. Plus, you will see IP addressing. We're going to do lots of stuff in class and examples in class. What is an IP address? Let's go ahead and just take a look at our own IP addresses. What I want you to do is go ahead and open up a command prompt, and I'll show you how to do that. And here's what we want to look for. Let me get these all here. Okay, we want to pay special attention to something called the subnet mask, the default gateway, and then in labs, we're going to learn how to change our IP address, our subnet mask, and our default gateway. But let me show you how to find your own, okay? There's a couple of different ways. So probably the easiest way is if you just go here to your command prompt or to your search bar, you can type C, oh look, mine pops right up. And there's my command prompt. But you may have to type it all the way out, command prompt. Okay, you can also type in CMD. CMD. So here we've got a command prompt. Okay. I'm going to wait while you do yours. You can keep the video running. Now I want to see what my IP address is. So I'm going to type ipconfig. All right. And here we can see I'm on my home computer. It's giving me an IPv6 link local address, which we'll talk about a lot in Module 12. But here is my IPv4 address. You can see it's a 192.168.0.23. Here's my subnet mask. And then finally, here's my default gateway. Why do I need a default gateway? Remember, a default gateway is an exit and an entry point on my home router. It's an IP address on an interface. Without a default gateway, I cannot have any access to the internet. I can't get to the outside world. We will be talking a ton about IP addresses. We're going to talk about subnet masks, default gateways. How do we find them? How do we figure them out? What are they for? Okay. Now, one more command I want to show you is ipconfig space / and then the word all. Or is that a backward slash? I don't know, this way, okay? Now, this is going to give me a lot of the same information. Okay, it's going to tell me what here's my IP address, my subnet mask, my default gateway. But see how there's a lot more stuff here? The other address I want to draw your attention to is this thing called a physical address. Now, a physical address will be a unique address for every device. Every single device has their own unique physical address, okay? This IP address, you might have it, 192.168.0.23. It's only unique to my local area network. But the physical address, these addresses, every single device in the world has to have their own unique one. This brings us back to this IP address. Now, I actually think let's just go ahead and take another break at this point. If you remember in Module 2, we talked about the SVI, the switch virtual interface. Notice Module 3 talks about it again. That's because that's how important it is that we learn and understand it. I do have another video that I'll be posting into the learning resources about how to set up the SVI, how to configure an SVI. It's a demonstration. Plus, we will do this in class together several times. Let's go ahead and take a break. The switch virtual interface. This is an invisible. It's not an actual physical interface or something that you can see. It's built into the software of an operating system. This is a way that we can add an IP address to a switch. The switch functions at layer 2. And at layer 2, all we have is MAC addressing. If I want to be able to manage a switch remotely or get into the switch from an in-band connection, I need to set it up with an IP address. That's why we have switch virtual interfaces. That's what allows me to be able to get into that switch in order to configure it from an in-band connection, or if I'm remote. Let's say that I am taking a little vacation in Payson and I'm the network administrator. Something goes wrong and I need to be able to get into the switch in order to do some show commands or add a configuration to it. As long as I've been able to set up an IP address for the switch virtual interface, I can get into that device from wherever I'm at. It's super important to understand this and know how to do this. Once I get that SVI video demonstration posted, I'll let you know, and keep your eyes posted for when we do this in class. And when we do this in a lab or a packet tracer, really give it some attention. Don't just rotely go through the steps. One of the things that I find students do that is a mistake is not taking time to read the labs and understand what you're doing. Instead, sometimes I see students just rushing through and just like, ah, da, 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 and they're not taking time to understand why they're doing something. One of the things I'd like to ask you to do early on is give it the attention that it deserves. That way, when you get to the end of however many weeks you are in this class, and you're asked what's an SVI or how do you set up an SVI, you're not going to say, well, I don't know, right? You'll actually know and you'll understand because you had been carefully going through the labs and with practice and patience putting in these commands for a switch virtual interface. Oh, and we have a documented tutorial. I probably already have the packet tracer posted. I'm sorry that I don't know that immediately, but I'll find out. Okay, we are at Module 4 highlights. Remember, what I covered in Module 3 is not exhaustive. There could be a lot of stuff in Module 3 that especially you may have never heard of and you don't know. It is still a great idea to go through Net Academy's Module 3. Don't rely that I was able to give you all of the information. It's a great beginning. It's a great start, but it might not be everything. Especially watch any videos that are in NetAcad because they're simple, they're usually not very long, and they really get the point across. Here are highlights for Module 4. Review the 7 layers of the OSI model, the 4 layers of the TCP/IP model, the PDUs. Then Module 4 starts with types of media and the characteristics, including the speed capabilities, the positives and the negatives. What are we referring to with types of media? Fiber optic, Ethernet, coaxial, what is a crossover cable, a straight through cable, etc. Here we're going to see more of this encoding, decoding, and signaling. The protocol suite module that we just went through gave you the basics, but encoding and decoding happens at layer 1. Well, Module 4 is all about layer 1. What is the bandwidth and speed equivalence? What are the different fiber connector types and speeds? Something interesting that's happened in the last couple of CCNA revisions is they've been adding more and more information about fiber optic cables and connectors. That's probably because that is becoming so common and popular now in the world of ISPs, telecommunication companies, etc. Copper cable standards and the wiring patterns. We may do an in-class lab and troubleshooting if time allows. We almost always have an extra credit assignment where you can actually build a copper cable. What is the data link layer? What are its responsibilities? How does it relate to layer 1? What about the MAC layer? What is contention-based access control methods? Okay, CSMA, collision avoidance and collision detection. Do you know the difference between full duplex and half duplex? What are the layer 2 standards? These are standards you do need to know, and you want to memorize these and make sure that you're able to recall them. Finally, what is the format of an Ethernet frame? Just like the OSI model, the TCP/IP model, and the PDUs are super important, and we'll constantly be talking about them and asking you about them in class. The same will be true about the format of an Ethernet frame. Reminder, watch any of the required videos. We post videos about binary to decimal, decimal to binary, subnet mask, network addressing, because the expectation is that you're watching those before you come to class, because then when we have a group discussion and we have activities around them, that will go faster for everybody and you'll understand them. Plus, if there's something you don't understand, you will be able to ask questions and we can work through that obstacle in class. If it's a question for you, it's very likely a question for somebody else too. Okay, we're going to see you in class. That is the end of this presentation. Remember to fill out the survey for Module 3. It's asking you what learning resources you used, as well as do you have any questions? Do you need clarification on anything? Typically, the stuff that we cover in these videos, we will not necessarily cover in class unless we know that it's a difficult topic or people are asking about it. Have a great one. Talk to you later.